Okay, lots of announcements today. Um, the next one is about CSUA, the Computer Science Undergraduate Association, and they're passing out these little pieces of paper talking about help sessions that they run to get you started using the facilities here. And there's one specifically for you called A Field Guide to Instructional Computing, How to Survive CS61A, which is the one that's called 61A up there. And then there's another one, What Do I Type Here? An Introduction to Unix. And both of these sessions are being offered twice, so you only have to go to one of them. Tonight, first the 61A one at 6:30, then the Unix one at 7:30. Tomorrow, the other way around. Today's ones are in 310 Soda, which is one of the classrooms, and tomorrow they're in 306, which is the big HP auditorium in Soda Hall on the third floor. And also, they're having their first meeting. If you want to be a member of CSUA, you can come. That's 6 o'clock, Friday, February 8th, in the Wozniak Lounge on the fourth floor of Soda. I'm not having an office hour tomorrow because of another event that you should know about. The Regents Lecture, which is a big deal. It's not something just that our department organizes. It's the campus selects some luminous scholar in some field or other to come give lectures, and they only do a few of them in a year, or one of them in a year, or something like that. And this one is Fran Allen, who is a big shot at IBM research, has a long and illustrious career. Her title is The Challenge of Multi-Cores, Think Sequential, Run Parallel. We talked about this a little already, how the efficient use of more than one processor is not a trivial thing. And there are a lot of current CS research efforts in trying to find ways to do it. And we talked about why functional programming plays a big role in that. And later in the semester, you'll be using MapReduce, which is Google's protocol for taking the ideas we're talking about this week, the higher order functions, and using them as the organizing principle for doing parallel computations. And you'll be doing a lab and homework about that. But anyway, if you're interested, come to the talk tomorrow. It's at 4 o'clock in Sibley Auditorium, which is in the Bechtel Engineering Building. It's the one that food place is on the roof of. Yeah, I think that's it for administrative things. So up on the middle two boards here are pictures of the main higher order functions that you know about so far for dealing with data. Each of these takes a sentence and does something to it. You're writing every for homework, I think. I wrote keep in lecture on Monday. Accumulate, you've seen in chapter 1 a different version that works on just numbers and steps through them using some function. But a generalization of that takes a sentence and accumulates all the words of the sentence using some combiner function. So every takes a sentence, looks at it word at a time, and transforms each word into another word, or possibly more. With every, depending on what function you give it, your function might output 2 words for each one word, and they would still all be gathered together. Let me show you what I mean. End of word, sentence, word. A, A, B, B, C, C, D, D. So here's a case in which you give every a function that takes in a word as its argument, but it returns a sentence, and all those sentences are strung together by every to form one big sentence. But the main point is that each piece of the input is transformed into something else. and you provide a transforming function to do that. Every's job is to make sure that that function is applied to every word in your sentence. Keep is a selection function. You take a sentence, and what it returns is not a transformed version, but a subset of that same sentence. And in this case, the function you provide is a predicate that's true if we should keep this word and false if we shouldn't keep the word. And then accumulate takes a sentence, a bunch of things, and using a function that can take two arguments and combine them in some way, produce one big result. So the usual combiners are things like plus or times or word, for example. You can say accumulate, did I spell it right? I hope so. Word. And that'll smush all the words together into one big long word. So these are three patterns of computation. If you've programmed before in other languages, it's the sort of thing for which you may be accustomed to using an iterative loop. You know, for I equals 1 to the length of the array, array sub I gets blah, 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 that sort of thing. And instead of describing it as an iteration like that, we describe the process as a transformation of the entire data set, the entire sentence, into something else, different something else's depending on which higher order function you use. And these are all three very, very common patterns, and they illustrate how higher order functions are enough of a tool to build most of the sort of looping structures that you want to use from other languages. And also remember that higher order functions themselves are not magic. They're built out of lambda and recursion, basically, to make them work. Is that a question?
Yes. What's the difference between accumulate and apply?
What's the difference between accumulate and apply? We haven't really talked about apply yet. There is no difference if the function you're using is one that can take variable numbers of arguments. Apply calls a function once and gives it all of the things that you have as an argument. Accumulate calls a function of two arguments, and it adds in one word at a time. So you take a result and add in the next word of the sentence, and then add in the next word of the sentence by calling the function repeatedly. So, well, there's no difference if the function that you're using is one that takes a variable number of arguments. But we can use this with a function of exactly two arguments. For example, let me think of a good example. You want to find the longest word of a sentence. So you would write a function, lambda of two words, that says, return whichever one is longer. And that's something that isn't built in as a primitive, so you don't have something ready-made that takes multiple arguments. You write one with a lambda that takes two arguments, and then you can use accumulate with it. Okay?
Same time we can say apply, and then max, and the whole list.
No, you can't, because if you apply max, you've lost the words. You now have just numbers.
No, we can't.
Yes. Anything that you can do with any particular tool, you can find some harder way to do. Yes. But accumulate is an easy way to do that sort of computation. There was a hand up over there. Yeah, he's saying there's a difference between accumulate and apply if you use subtraction, because although minus does take multiple arguments, it does something funny with them. Frankly, I would never use minus as an accumulating function because I wouldn't be sure how it associates, and I would be scared. Basically, you use it with associative functions. But I don't want to get sort of bogged down in details like that right now. the point I want you to make is that these pictures here are pictures of three very common things to want to do. Transform the elements of a set in some way, like the words of a sentence, select some of them, or smush them all into one final value in some way. And we have higher order functions that do those things. And I also showed you last time the functions that return functions like makeAdder and compose, and how you can use those things to have a sort of algebra of functions. So you can write a bunch of little tools that take functions as arguments and return different functions and never actually look at anything other than a function until, you know, a pretty late stage in your computation. Okay, on to let. What we're talking about is a new special form called let. And I'll tell you the secret right at the beginning. What it is, it's just a syntactic rearrangement of two things. One is a lambda expression, which creates a procedure, and an invocation of that procedure. So the situation we're looking at is some function, lambda of ABC, compute some value, and we call that function with three arguments, 7, 92, 100. They don't have to be numbers, they just happen to pick numbers this time. It depends on, obviously it depends on what this function does. But what we're going to show you is an abbreviation for this two-step process and lead up to it by showing why you would want such a thing, why this comes up in practice a lot. So the example that I have is boring, I apologize, but it's the classic one, namely solving quadratic equations. And a quadratic equation typically has two roots. So, and in all cases, as it says in the comment here, we're talking about quadratic equations with real roots. And if you want to generalize it for other things, that's interesting, but not interesting for the purposes of this discussion. So let's only think about equations that do have real roots. And there's this formula, minus b plus or minus the square root of b squared minus 4ac over 2a. Because of that plus or minus, we get two answers. So our function is going to return a sentence with two numbers in it. And there's an example up here where I call roots with the arguments a, b, c, which are the coefficients of x squared, x, and constant term. And this particular equation, x squared minus 5x plus 6 equals 0, has the roots 3 and 2. Okay, so everybody clear on what problem we're solving? And if you look at the code, we're returning a sentence. So here's the sentence, a primitive constructor that puts words together into a sentence. And here's minus b plus the square root, there's the plus the square root of b squared minus 4ac over 2a. And then the other argument is minus b minus the square root of b squared minus 4ac over 2a. This is the only difference between those two formulas. And we take those two results and put them into a sentence. Okay? Well, this is completely straightforward, not too hard to read, but kind of inefficient. We're going to talk about efficiency just a little bit next week. And let me acknowledge right off the bat that the amount of inefficiency here is not something that anyone would really worry about these days unless you're trying to solve, 3 billion quadratic equations or something. But let's just pretend that square root takes even longer to compute than it does. Okay, pretend it takes 6 seconds or something to get a square root. So we'd like to do it once instead of twice. So how are we going to do that? Here's a procedure that's equivalent to the one that you saw before, but it only does that square root once. And the way it works is the computation of the square root is the first thing that happens here. This is the body of roots, this line. And it calls a helper function, roots1. And the argument to that helper function is the square root of b squared minus 4ac. And as you learned last week, scheme uses applicative order rather than normal order. So this square root expression is actually computed before we call roots1. And the argument that roots1 gets is the value of that square root. So up here in the definition of roots1, it's an internal define. I've given it the formal parameter d, not because that's the next letter of the alphabet, it stands for discriminant, which is what that square root thing is called for quadratic. And so we still return sentence of two things, and there's still this difference between the plus sign here and the minus sign here. But now, instead of computing the square root each time, we just say d. So this shows how we can use helper procedures to give us the opportunity to compute something once that we need to use more than once. We compute it right off the bat, and then we call a helper function, which takes it as an argument, and we use it in the helper function as needed. So questions about how we wrote this one? Are you happy with this? All right, well, this is okay. This is not such a bad way to write it. You can sort of work out what it's doing. But I'm annoyed at the fact that I have to give roots1 a name, because this clearly is a function that's only ever going to be called in one place, and it's only called once in that place, namely, here's the call to roots1. So I'm annoyed at writing a name for it, and I really want to make it a lambda expression. And I can do that too. And I get this procedure. So I'm going to define roots of a, b, c to be open paren, and then open paren lambda. So everything from here, the second parenthesis, to the matching closed parenthesis down here, all that is the lambda expression that is equivalent to the definition of roots1 that I had earlier. And then the outer parentheses invoke that with square root of b squared minus 4ac as its argument. Well, I'm happy now that I didn't have to make up the name roots1, but this is looking pretty ugly. And you have to really think about it pretty hard to understand what the sequence of events is, namely that this last line down here, oops, is the thing that happens first. All right, we compute this, and then we call that procedure. So this is kind of an ugly thing, and guess what? It's exactly this ugly thing. Right? It's creating a procedure with lambda and immediately calling it. So this is the reason why you would want to do that. Basically because in your roots procedure, you want a local variable, d, that isn't one of the arguments to roots. So if you've programmed before in other languages, which many of you have, you would expect to have inside procedure roots a declaration of a floating point variable d, and the first thing you would do is assign a value to it, which would be the square root of blah, 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 and then you would go on and use it. Well, as you see, we can do that in Scheme. This is an example of the fact that all you need is lambda to create any control structure you want. But this is a very, very common one, and this is a pretty ugly way to do it. And so we have an abbreviation for this. See if I can fit both of these on screen at once. Well, almost. There. So up on top is the way that uses the lambda expression and then calls it, and on the bottom we see the abbreviation. which is let. And then this is the other case besides cond where parenthesis means something other than procedure call. This parenthesis right here, which ends at the end of the line, is grouping any number of name-value pairs. In this case, it's only one of them, but let me show you how this example with ABC would look as a let. You would say let parenthesis, and then inside that there are some sort of special parentheses. Name, value. Name, value. Name, value. And then close off that whole group of what's called bindings. A name and a value, an association between those two is called a binding. So we have here a group of 3 bindings. All of the parentheses that you see up here are special syntax that don't mean call a procedure. Except for this one, this is an ordinary thing, except that let is a special form, clearly. And then you have the body, same as the body of the lambda expression over there, close parenthesis. Okay? So these two expressions on the board are equivalent. The lambda and its invocation and the equivalent form let, and then we take the formal parameters from the lambda, ABC, and the actual argument expressions, which in my example were just numbers, but they could be complicated calculations, like this is the square root of b squared minus 4ac is one of these. And we combine each formal parameter with the corresponding actual argument expression, and that makes the let really easy to read. We can read it by saying, oh, okay, I get it. A has the value 7, B has the value 92, C has the value 100, instead of having to look in 2 different places for the names and the values. And then comes the body of the lambda. And the let doesn't just abbreviate the lambda, it abbreviates this whole thing, which is a lambda that's invoked with arguments. Okay? Questions about this? So the way to remember it is let is lambda plus invocation. Kind of. Okay? And finally, here's an example where I actually used the let with more than one formal parameter and actual argument expression, because I decided that while I'm computing the square root only once, I might as well compute only once minus b and 2a. So don't be confused by this notation right here. This is just a word. It's a variable name, minus b. Okay? Scheme doesn't know that minus sign has a special meaning in here. It does know that minus sign as a symbol all by itself is the subtraction procedure. So here we're calling a subtraction procedure. Here I'm just giving a name to a variable. And similarly with 2a, that's just a word. And so that makes now the body of the let much smaller and also more readable. We take minus b, I'm looking right here, minus b plus d divided by 2a, and here is minus b minus d divided by 2a. Okay? It's really easy to get confused and to think that let and lambda mean the same thing. So that's why I'm really pushing on this, to make sure you understand that let is a 2-step operation. There's an implicit lambda in here to create a procedure, And also implicit in the let is the invocation of that procedure. So we're making a procedure that's only going to be called once. And the reason for doing that is just as lambda and procedure calling are our mechanism for dealing with what would be iteration, looping in another language, lambda and procedure calling provide our mechanism for having local variables, for assigning values to variables just long enough to compute whatever the body of the let is. Okay. Why are local variables good instead of making everything a global variable? Some teacher probably drilled this into your head in high school, but the idea is if everything is a global variable, then this piece of the program is likely to mess up that piece of the program in some way. Whereas if the variables only exist inside a particular scope, a particular piece of the program, then whatever happens in the rest of the program can't get in the way. Questions? Yes? Are we ever going to use let star? Okay. Yeah. Let me sort of motivate the question before I answer it. And this is another thing that students sometimes get wrong about let. If you look at the sample midterm ones in the reader, this is a hint for the midterm. There's very often a question of this sort, where people try to make these bindings be sequential in time, like this. Right. AB7, BB plus A3, and then the body will be, let's say, times AB. And the person who writes this expects to get the answer 70. Right? We make AB 7, and then B is 7 plus 3 is 10, and then we multiply those together. Does not work. And the reason it doesn't work is, let's see what this expands to. If we remember that let is lambda plus invocation, that bad expression over there, the lambda expression is lambda of AB times AB. And now we're invoking that with the arguments 7 and plus A3. Well, how does Scheme do procedure calls? Answer, it uses applicative order, which means what? What's the first step? Evaluate all the sub-expressions. So we evaluate this sub-expression, its value is a procedure. We evaluate this sub-expression, it's just a number, so its value is 7. We evaluate this one, and we have a problem, because there's no variable A in the scope in which we're doing this evaluation, or maybe there's a global variable A that's left over from some previous computation, but if so, it doesn't have the value we're expecting. Okay? So all of the argument expressions are computed before we get inside this procedure and actually associate these values with the formal parameters by substituting the values for the formal parameters in the body. So we're evaluating plus A3 in a context where there is no A, or at least it isn't 7. So this doesn't work. You can't have bindings, each of which assumes the one before it. That's against the rules, because it doesn't make sense. We could, however, solve that problem a different way. A perfectly legal way to do what that's trying to do. Oops, there's no board here. Okay, let me use this one. Sorry, HCAN. Hope everybody got that. I could do this. I could let A be 7. And now, in the body of this let, I'm allowed to use A, which will have the value 7, And so what I'm going to do is another let BB plus A3. And the body of the inner let will be times AB. Close the times, close the inner let, close the outer let. This works. Because it's something that people want to do, and again, because this is pretty ugly, one of the problems with things like this is that you get pretty far over toward the right margin, because everything gets more and more indented, you know. So because it's something people want to do a lot, we have an abbreviation for nested lets, and it's called let star. And so you can write an expression that looks exactly like that one that doesn't work, except instead of let, you say let star, let with an asterisk. And again, this is just a 4-letter word. This doesn't mean times or anything. Are you feeping at me? Okay. And what the let star means is just however many nested lets as there are let variables. Okay? Does that answer your question? Will we use it? It'll come up from time to time. Not usually very much, because mostly it's not the right thing to do. I mean, sometimes it is, but mostly if you're thinking in those terms, you're making the problem more complicated than it has to be. That's a heuristic, hand-wavy rule of thumb for you. If you look in the scheme reference manual, which you have in volume 2 of the reader, you will find actually 4 different versions of let. And besides let and let star, there's let rec and let rec star. I'll talk about those just for a second. These are solving another problem that stems from the fact that let abbreviates a lambda in a procedure call, and a procedure call scheme evaluates the actual argument expressions first, before we call the procedure. Suppose the actual argument expression is a lambda expression that's trying to create a recursive procedure. In other words, I have to erase something. I'll erase this. I wish that sliding board actually slid properly, but they'll fix it eventually. Suppose I want to say let factorial be lambda of some number. If n equals 0, return 1, otherwise return n times the factorial of n minus 1. And then, what's the factorial of 5? Doesn't work. Why doesn't it work? Because this lambda expression is evaluated outside of the implicit lambda expression made by the let. So in the scope that has this lambda expression in it, in the piece of the program where this lambda expression is evaluated, this exclamation point doesn't have anything substituted for it. There's no binding for this exclamation point. We look for a global variable named exclamation point, and maybe we find one, but probably we don't. And even if we do, it probably isn't what you meant. Okay, so you can't create recursive procedures in let bindings. So there's this thing called let rec, and the way it actually works is way too complicated for me to take lecture time on, because we're never going to use it. But if you're interested, in the scheme reference manual, there is an implementation of let rec, which you aren't going to really be in a position to understand for another month or so, until we talk about object-oriented programming and assignment of values to variables and so on. In other words, we have to get out of the realm of functional programming in order for... If I bring the mic closer to me, does that do any good? No. Okay, earth to control booth. Turn my volume down. Okay. Can you still hear me? Okay. Right. So, LetRec does this very, very complicated thing so that you can make this work. And LetRec star is a combination of the two. It does nested LetRecs, one for each binding. Okay, other questions? No. All right. So what's this let topic doing in this week when we're supposed to be talking about higher order functions? And the answer is, this week we introduced lambda. And let is just a nice little extra piece of notation, what language design people call syntactic sugar. Meaning it's a notation that we could perfectly well do without. It doesn't improve our ability to do anything because we could write a lambda expression and a procedure call around it. But it looks nicer this way, so we have let. But in order to understand let, you have to understand lambda. Another thing about let, and this is for people who've programmed in other languages, and again, I'm not saying anything you don't really know. I'm just saying it in different words. Because of this let equals lambda plus invocation, the bindings, the association of names with values are only valid inside the body of the let. Okay, because the way we do things is we compute the actual argument expressions in order to get actual argument values, and then we plug in the actual argument values into the body of the procedure in place of the formal parameters. And therefore, we no longer see the formal parameters, and all of that whole operation only happens for the body of the let. So if you do this let, and then later on you do something else, you can't expect those variables to still be available to you. Yeah?
What error will we get here? Will we get unbound variable?
What error will we get for this case, the LetRec case? Yes, unbound variable, exclamation point. Unless you have exclamation point globally defined to be somewhere else, something else. Other questions? Okay. By the way, preview of coming attractions. Everything that I've said about substituting values for names and everything, that's all a lie. As we'll see in a couple of weeks, no, in about a month and a half maybe, the substitution model of evaluation only works if we're doing functional programming. So when we start talking about other programming paradigms, we're going to have to use a more complicated model for how a scheme evaluates expressions called the environment model, which is really true. But for the next month and a bit, what we're saying about substitution is true enough, namely the results are the results that you get from the substitution model. And that's an easy way to think about what's going on. Okay. Wow, have I really said everything? Oh yeah, just the last reminder. We talked last time about first-class data and the principle. This is not working well at all. Unless it's somebody else making that beeping. Is it someone else? Are you beeping in the back? Anyway. Ringo, is that you buzzing? Okay. Last time we talked about first-class data, and what it means for something to be first class is that it can be the value of a variable, an argument to a procedure, the return value from a procedure, and a member of an aggregate. And everything that's data at all in Scheme is first-class data. So every kind of thing that we can have, including procedures, can be used in all those different ways, and we'll be doing that over the next several weeks. In almost all programming languages that aren't descendants of Lisp, procedures are not first class. There isn't anything like Lambda. You can't create a procedure. You can't write a procedure that creates a new procedure and returns it and then use that new procedure somewhere else. And the reason for that is that it's a little hard to implement efficiently. So that's the aspect of Lisp-related languages that are a little harder for the compiler people to deal with than languages like Java and C++ and C and Pascal and BASIC and all those other things you know. So it's a little hard to do, and you won't really understand why it's hard to do until we talk about the environment model of evaluation. You see what actually is involved. And you'll understand it even better when you take 61C and you can start seeing what the computer actually does in response to these higher level, more abstract language constructs. But it is a little bit tricky to do. You'll see it's not very hard. We're going to write a scheme interpreter in this class before the end, and it will handle Lambda doing all the right things. But the one that we write is not going to be incredibly efficient. If you want it incredibly efficient, that's a little bit harder. I think that's it. Last chance for questions. Yes? This week's extra for experts, can you use letrec? No. So this is the one about how to do a recursive factorial function without being able to give it a name. And it's true, if you can use letrec, that would be a simple solution. But no, the idea is all you have is just plain old lambda. And see if you can still do it. It's a really hard extra for experts. It will not astonish me at all if nobody gets it. But many of you will understand the solution when you see it. So it's worth you spending some time banging your head against it so that when the solution shows up, you can see how brilliant it is. And I'm not the brilliant one, so I'm allowed to say that. Other questions? No, everybody wants to go home. All right, see you Friday.